Good afternoon. This is Harbola. All of you know him, but just for the sake of talking. He has done this.
I don't think
Okay.
they can hear.
So
You should come forward.
yeah. Please come. Why you are
Morning also I put
behaving
link in
like a
front.
criminal?
Oh, there
So
are
he did his
places.
PhD from City University. After that, he did postdoc. Then we moved as a
Cracking door.
for joining IIT Kanpur. There and research and also he is a well-known researcher. Of all, he is very well-known for his contribution and of various types of AFT and also functional. Very well-known in that field. And today he is going to talk about what Max Planck was.
Okay, thanks. Thank you. And it's always, I mean, I've been coming here for like 20 years now, more than 20 years. It's always a pleasure being here. Friends, teachers were here. So, this is the government. This is a what I'm talking about is what Planck could have done. So before that, I have to explain why this topic. And it is historically very, very important because what Planck did was started a revolution, and because he gave the concept of the oscillators should be quantized. So I should actually tell you why oscillators are quantized, and then what he did in the process. I'll talk about that. And there has been some. So he was criticized by Einstein and others for the way he used Boltzmann statistics, and also the other criticism was that, and that I'll comment upon, that he was using electromagnetic theory as given by Maxwell, combined with the quantum concept, and that is an inconsistency. Using a classical result to get a quantum result. Planck himself was kind of he was very uneasy with the whole thing, and for a long time he did not admit. He tried his very hard to fit this whole thing into classical stuff because he was a student of Cauchy's, and his main thing was second law was the ultimate point. And so this period from 1900 October when he proposed the black body radiation formula, and then he tried very hard to interpret it. Later in his autobiography, he has written that this is the most intense work he did in his life. Because also, I have to tell you that he did not believe, he was a classical physicist, so he did not believe in atomistic theory, which was coming up at that time. He did not believe in Boltzmann's theory, which was also coming up at that time. But once he got his formula, and that he derived from his second law of thermodynamics, from entropy, he had to find an interpretation, and then he took to Boltzmann's stress. Other thing about Planck, which is worth learning, he was evolving all the time. First, he was not an atomic, he did not believe in atomic theory from a strict point of view, but then he worked in chemical physics or physical chemistry at that time, and he changed his view. And then when he learned when he had to find an interpretation, again changed his view. So this is something worth learning from Planck. The other thing which is worth learning from Planck is tough time he went through. He lost his eldest son in First World War. The son had gone for a war, for the fighting. So that was in 1917, right, if I'm not mistaken. 2 years later, he had twin daughters and then one more son. And before that, his wife had died after 22 years of marriage. Then his son got killed in First World War. His one of the daughters died during childbirth, and 2 years later, the other daughter also died during childbirth. And his youngest son, Erwin, who he was very close to, he did a lot. After losing all his children, he was very close to him. They used to play music together and all that. that son of his was executed by Hitler. So despite all that, the tough time he went through, uh, he kept going. He kept going, and physics was important for him. And just for historical facts, uh, he is the one who actually he was the editor of Another Physics, one of the editors when Einstein submitted his papers. He is the one everybody was not believing Einstein because he had come up with relativistic theory and all that. Planck is the one who pushed it again, his foresight. And he's the one, as proctor of Berlin University, the first woman lecturer was hired, he pushed for it, Lisa White. Okay, so he's quite a great man. I mean, it's not, and then he was president of this Kaiser Wilhelm group also, which later became Max Planck Institute. So he respected a lot. He was taught by the Americans after Second World War, or during at the end of Second World War, when he was 87. He was really in bad shape, taken to a hospital and all that for intervention that he was involved in coming home. But the man was really something. So I have been reading about him for a long time, and I mean, one of my fascinations with personal business has been the development of quantum theory. I've worked out many of these papers, and somehow I did not believe him. So there have been, I would tend to say, insinuations, and by no other than science historian called Thomas Kuhn, who said that Planck probably had calculated, and I'll show you how he arrives at that conclusion. And that somehow does not sit well with it. If you read about Planck, he was such a person who was never touch a low-level problem. He would go for very high-class problems. He himself was very well brought up, belonged to a very good family, so he had his values were very, very strong. So he wouldn't do that. Probably, he never believed. He learned Boltzmann's statistics within a month or a month and a half. He tried to come up with a calculation, and it matched his. So in excitement, we have given it, but his conclusion that oscillators have to be quantized is absolutely right. So this is what has been driving me, and I was wondering how, following exactly his path, one could see that what he did was actually correct. So that's one thing I'll touch upon. On the way, I'll also comment on what Einstein did and how man whose name the center is on, how he fits into it. So let's begin, and I'm going to make it chalk in this thing because I won't make mistakes, and please correct them. So it's a very proud moment if you remember all these things. It's really nice. So I'm challenging myself also. So what Planck did initially when he took up this problem, remember Wien's formula was already there. And then right, I'll also remind you what I mean. Wien's formula said that the energy density, spectral energy density, that is at any given temperature, what is the energy content between u and u plus d nu, has to be of the form u cube, a function of nu by t. Thus, just to remind each, particularly students who are doing research now and may have forgotten all this, is the energy content. Per unit volume, so it's density, and per unit frequency, or in the range. Nu and nu plus. All right, and the density comes out to be from you can work it out like kinetic theory, c by 4. Now, what Planck did when he came, and then after that, Wien has derived his formula. Once he had this, so before doing this nu by t factor comes because he had this formula, lambda max t equals constant. And then he said that maybe the radiation coming out is proportional to the kinetic energy, and therefore has to be of the form e raised to minus some constant, right? Let's call it b, mu, and to have this form he did this. And outside he had some a. This was Wien's formula, right? So he had this formula. It was beautifully up to some limit, right? And that's when Planck came to the picture. So this is Wien. Now, when Planck comes into the picture, he wants to analyze the whole thing to second law. He's absolutely crazy about second law. Second law money was God. Even for when he writes his autobiography in 40 years later, he says, "For me, second law is the ultimate. I just want to save time." So he said, "Let me look at it uh, from second law point of view." And there's also a lesson for all of us in this. And he says in his autobiography that actually I decided to look at this problem from a very different perspective, from the entropy point of view, and therefore nobody else was thinking like this. Therefore, I was in no rush. There was no competition. I could be leisurely and work on. So that is a lesson for all of us that look at things from a different perspective. Then you don't have to rush. You can take your time. You can work out things properly. So what he said, let us look at this. So his main thing was that the second derivative of entropy with respect to this had to be negative. That will imply maximum entropy, and therefore you achieve it. All the black body formula have to be consistent. So he looked at this. He said, let us derive the entropy formulas. So from here, this is U. Oh, before that, one more. So before he started on this problem, he had derived that the energy density in a black body cavity. Once I know energy density, I know the intensity. This is Stefan's law. Has to be of the form 8 pi u square over c cube e bar, where e bar nu, he assumed there are virtual oscillators here. So I'll make them like this. In the oscillator, there are these virtual oscillators with frequency nu, and they have average energy E bar nu. Then he considered equilibrium between the radiation here, whatever they are damped oscillators because they're radiating. So if you consider the equilibrium gives you this formula. Very happy with this. You can also derive the same formula using counting the modes and all that, but we'll not go into that. We will see the point of view was this. So this is that coming from electromagnetic theory. Consider a wave coming with intensity E square and all that, and balance with the oscillator which is radiating out, and do this. Notice something beautiful in this. It is independent of the damping constant of the oscillator. So the final result is very good. Once he got that, he said, let me work out entropy from here. Alright? So you knew is A nu cube e raised to pi minus b nu over kt, which is 8 pi nu square over c cube e bar nu. And therefore, besides these constants, this is nu. So E bar comes out to be nu e raised to minus b nu by kt, and there's some constant. Main thing is, I take E bar nu by nu, take log of that minus log of c is equal to b nu by kt minus I. And I've taken log on the both sides. I've taken log on the both sides. Okay. This will be plus. And therefore, 1 over t is equal to k also was a constant, but nonetheless, I mean, I'm writing this k, but in fact, I should just write b nu by t. K was also derived later. So 1 over t is 1 over nu log of E bar over nu. Okay? And therefore, dE, and this is ds by dE. Right? ds by dE, and there are some constants. So into s by dE squared is going to be 1 over E bar. some constant here. Let's write some constants. E is
So in the definition of E bar, C is just a constant.
C is a constant. So I'll put a minus sign here. There's a minus sign. This is less than 0. He's okay. So he said Wien's formula is consistent. Right? So that's one thing he checked. Then when he came up with this formula, one day his friends, Liver and Shine, they come to talk to him and they say, look, in one limit, when you go to nu by t, limit of nu by t becoming to 0, actually Rayleigh's formula is. So Rayleigh says that this is 8 pi nu square over c cubed times kbt, proportional to t. And you work out d2s by d square from here, because from here this is again 8 pi nu square and all that. So you get d2s by dt square is equal to minus 1 over e square. So in one limit he has 1 over e, one limit has 1 over e square, and he says now let me interpolate. And then the formula probably will be correct. So now he says this. Now he says, let me write this d2s by de square as equal to 1 over e, some constant a over e, b plus a. This does an interpolation formula. Okay? This then is equal to minus a over e minus 1 over b plus e. Let me see. You want to cancel something? 1 over. So you get minus 1 over b. So this will be minus a over b. Not doing all right? You get e cancels. You get b cancels. And yeah, this is it. So then he says this j by de therefore is equal to minus a over b log of e minus log of b plus e, which is a over b log of 1 plus d over b. And you put this equal to 1 over t. Lo and behold, you get e equals some constant divided by e raised to let's work it out for not cheat. So this is 1 plus b over e, therefore is equal to b over kt e raised to. Right? And this gives me b over e equal to e raised to b over kt minus 1. E equals b over e raised to bt, b over kt minus 1. Right? Pure interpolation. And once you get that, therefore, from his previous formula, u nu t has to be 8 pi nu square over c cube b over e raised to b over at minus 1. As simple as that. Now he says, by Wien's formula, you get u nu t had to be nu cube proportional to nu cube f nu over t. Therefore, t better be equal to some constant which I know is h. Now, nu. That gives you 8 pi nu square over c cube h nu by e raised to h nu. That's Planck's formula.
A. Yeah.
Oh no, no. So he's writing a B. He writes a lot. He writes a lot about.
So B is
Equal to
He writes a lot about how A should be some constant, which he says should be Planck's constant. But there is another way to do it, which I strongly said. I'm going to give you that argument. You see, if you go to the limit nu by t is very small, you go to this Rayleigh-Jean's formula, which is correct,
which has
and which is r by n. Right, that's the simplest argument, but he goes around quite a lot. That's why. By the way, the name Boltzmann constant was given by Planck. Right? So he does this, and then this fits beautifully. Now we had two constants here. We had sigma experimentally determined the Stefan Boltzmann constant, and we had this lambda max t equals b after some constant. With these two constants, he could determine these two constants. So everything was done. And once he got this is the first time in history he got n also. Avogadro's number was not available before that, it was just a concept. So he did that. Once he got Avogadro's number, he did one more thing. He divided Faraday's number by Avogadro's number, got electronic charge. Which is also very correct, obviously. So he could get H, K, and Avogadro in one shot. Okay. Then he says, I've done this, but if I stop here, there's a happily interpolated formula. I have to interpolate. That's where he turned to France, the Boltzmann response. He learned it and then did it. I think this formula had come in June or something. October he came up with it. So I'll come to that, and that will be the criticism also. Okay, so any questions so far? This is plain interpolation.
So I have one point.
Yeah.
This energy density in
Yes.
so factor mu square, 8 by mu square. So, I mean, what is the argument roughly?
Argument is very simple. Argument is that this electromagnetic wave is coming, is interacting with some virtual dipoles in the black body, which are radiating, and in equilibrium, whatever radiation is coming in has to go out. So everything is at temperature T. And you treat the oscillators, these electromagnetic oscillators, as the dipoles.
That will mu square from.
Yeah, because yes, it is some.
No, so I'm asking because the whole controversy actually was, I mean, regarding this factor only.
There's no controversy as far as Planck is concerned, because Planck is using electromagnetic waves. There are two polarizations.
Now I'm not talking about 8 but mu square.
Huh?
Mu square.
In
because
mu
whole
For news there was no controversy. News there was no controversy.
8 had a controversy.
8 had a
Eight had a
controversy.
controversy as well as mu square.
No, 8 also did not have a controversy. 8 came controversy because he told Bose to cut the micro.
Exactly.
He said polarization, Einstein said polarization, Bose said spin. But otherwise, there's no controversy. It can be derived.
No, controversy in the sense that nobody, nobody could find out that mu square quantum mechanism. Probably, I mean, yeah.
No, but that's not the point here. Point is very different. If I do, and this calculation is absolutely correct. You take electromagnetic waves coming in a cavity, assume there are oscillators, do the balancing act, you get this answer. There's nothing wrong with this. They're absolutely correct.
The oscillators are done, then how can equilibrium be established?
Oh, because they are receiving energy constantly from this electromagnetic wave coming in. That's exciting them. And then they're getting damped. So it's a steady state.
So damping is radiation.
Radiation. That's why you can equate it.
This expression, is that unique or can different form also be taken?
Or which?
Extrapolation.
This one.
Yes.
This is what he did. So it is unique Planck. I'm just repeating what he
No,
did.
this is your
Interpolation goes, it seems.
yeah.
How
You are
else
talking
it
about
can
this take care of interpolation.
Yes.
But can the different form also take care
I have
of
no
that?
idea. This is what Planck did.
Yeah, that's why I'm asking whether this is not derived something different.
No, so no, he took two limits.
yeah.
He said two limits. So how do I get? If E is very large,
Yeah.
if E is very large, I should go to this. If
Yes.
E is very small, I should go to
Yeah,
this.
yes,
That's a-
yes, yes.
So that, and he comments. He says This is the simplest interpolation scheme and it will remain an happily interpolated scheme. So I have to find an interpretation. He says that in his paper. He is very well aware of what he's doing. Except that it fits beautifully. In fact, you should type Kobe experiment on Google. 1992. You will find one single curve. You will find a curve like this. This is theory, experiment, and the error bar is within this thickness. So he says that it's a happily interpolated formula. That's it, nothing more. But it will remain so unless I find it. Then he realized that I have to go to post.
No, sorry, how did he interpret E?
How did he interpret?
H.
What is H?
H.
He is not interpreted. In fact, he struggled with it till 1920s.
So, did he recognize that it's a fundamental constant sort of?
Later.
Only.
But initially he tried, see, as I said, he always tried to see a classical picture with a classicist.
Right.
So he kept saying, what is it? So, but later his contribution also is, once he recognized the fundamental constant, it was he who gave the idea that H and E can be used to define universal constants, universal measures of length and things like those, which will be independent of what we do.
No, also the crux of the matter is actually guessing that U mu equal to, I mean, mu square E mu, right? And could he?
This is not guessing, this is derived. It's not a guess.
No, derived in the sense, I mean, when he found out E mu, I mean, sort of back calculation, right?
Which one? No, अभी कोई back calculation नहीं है. He knew he's just interpolation.
Ah, E mu is the interpolation.
Yes.
Right?
From
No,
experimental
I thought that-
results.
No, he could have got it through, I mean, actually assuming that it's a average energy of harmonic oscillator.
No, but that's what he did. He said that energy of harmonic oscillator is, this is 8 pi mu square over C cube E bar mu.
No, but what is E mu?
E nu is the average energy of the oscillator.
No, but for that you have to use Boltzmann statistics.
No, he has not used it so far. This is what he did.
Then,
I'm not telling Planck what to do. He did this.
or it's a back calculation.
That's your judgment.
So do you think that assuming this oscillator
Right,
already means a microscopic
right,
structure?
right.
What is that?
So I think he's going to say that,
Any assumptions?
yeah, you are making assumptions about the microscopic structure of the black body. So in some sense you are having an
No,
understanding.
no. I could have had this black body and put an oscillator here. That's what it says. These are virtual oscillators. Okay. So,
So is it more like saying that this black body is equivalent in spirit to a bunch of oscillators, but not
no,
exactly
so
made out
see,
of?
after all, black body is at a certain temperature. It is radiating all the time, and there is radiation inside. How does it maintain that steady state? The radiation coming in, radiation goes up.
You also said that he identified 8 to the 120.
Must be.
So when was the I thought that when photoelectric thing came about.
Photoelectric effect. By the way, that's why Bose's contribution is extraordinary. Because even in 1930, Planck took Einstein to Berlin University. He recommended him, and in a recommendation he wrote, "He is a fantastic scientist. Although he sometimes overshoots, he over-hypothesizes. For example, in his hypothesis of energy quantum."
So who actually identified that this age is same as the age of Einstein?
Einstein. Yeah. He did that in 1905. There is Annus Mirabilis. Okay. So once he got that, then he said, now next calculation was very simple. He said, now I have to now find the Boltzmann statistics. So what he said, let me assume that at frequency nu, I have to divide energy into small elements. So that's how you do counting in Boltzmann statistics. And for kinetic theory, you take that element to be going to 0 at the end. Right? So small elements epsilon. So there are going to be E, suppose there are n oscillators. N E bar, I'll just write E, I don't want to keep writing bar name. Upon epsilon elements. which have to be divided among these n oscillators. Right? So I have this many elements which have to be divided among n oscillators. How many ways can I do it? So the problem is very simple. I have these p elements, these p elements, and I have to divide them among these n oscillators. So I'll take these n minus 1 partitions and count how many ways. So all the permutations through this, which I can do, that will be the number of ways I can divide. That comes out to be very simple. All these elements are number is n plus p. These are called p minus 1 factorial divided n minus 1 factorial. Because these p are indistributable, these are indistributable. Okay, he says this is the number of ways. And if this is the number of ways, let me take the log of it, and that will be the entropy. Log of W is one I can ignore, n plus p log n plus p minus n log n minus p log p.
This is being done by PLANCK.
This is PLANCK.
So at this point, yes.
Now he is deviated. Now he is trying to find the explanation.
But he is accepting, coming to accept Boltzmann.
Yes, yes, he had to do. Right. So now I can write this. I can write as n e over epsilon, and I can take out 1 plus e over epsilon log of n plus n 1 plus e over epsilon log of 1 plus e over epsilon. That's the first term, minus n log n minus n p is e over e log of n minus n log of e. This is the entropy. And entropy per oscillator would be this. So you can actually see why he was so excited about that formula which he obtained, this one. Because with this is a constant for a given nu. You could focus only on this one oscillator. That's why he was very excited about this. So now you can cancel certain things. E by E log n, E by E log n, this whole term cancels. So you end up getting 1 plus E over epsilon log of 1 plus E over epsilon minus log of E over epsilon. Alright? Now he says, so this is entropy. Alright? Now he says Wien's formula is Wien's exact thermodynamic derivation tells me that E 8 pi nu square over C cube E. This I did earlier, but I'll anyway do it again. Nu cube F mu over T. Right? So F mu over T is equal to E over nu times some constant, right? Some 8 pi over C cube. Let's write it. And therefore, mu over T is equal to some other function E over nu times 1 over. Right? Just inverted this. This is a function mu over 2, invert this. Mu over T would be equal to some G E by nu and 1 by nu difference. And this is nothing but Ds. And therefore, Ds is d E by nu, d E by nu. Therefore, it's a function of E by nu. right? Now compare this. If I compare this, ideally when I'm applying Boltzmann statistics, I should take limit epsilon going to 0 in the end, which we do in driving kinetic theory. I can't do that. So epsilon has to be. Therefore, the energy elements of an oscillator have to be quantized. Have to have form H2, nothing else. And then he gets his formula. Obviously, then all that EVT and all that becomes 8 pi nu square over C cube, H nu over E raised to nu by whatever, AT minus 1. That's the exact. So now the criticism. He's just counting the number of ways. He has not maximized any number of ways, which Boltzmann statistics says that we count all the number of ways and maximize it. He has not applied any e raised to minus e by kBt. He has not done. So no maximization. And third, inconsistency between EM theory and quantization. EM theory, you're using a continuous theory. So energy of EM, electromagnetic wave, is continuous. But it can take only a quanta in the oscillator. This is very inconsistent. So this is what gave Einstein the idea that actually this should also be quantized. Okay, and he does it beautifully, again, using B's form. So these three are the controversies. So he has not used any maximize that occupation should be e raised to minus e by kBt. He has not used the maximization. So this is why people said when he had derived this, he had gotten through his formula, this kind of form, so he actually back calculated. That was false. He says that. The other people who say that we have back calculation, because you see when he was doing this interpolation, through that he got a formula like this. Okay. But there, because he was doing through Wheel's formula, he got a new. So he said, how do I fit the two? On the other hand, people say, there are other historians who say that, look, I mean, thing is, he himself admitted later it was an act of desperation. I had to find an answer. I mean, he was, again, a classicist who was very stuck on the values. He said, I can't just use a. So he got excited. So, that's, nobody knows that. But he was criticized. Einstein himself said, Mr. Planck is doing all this. Either Boltzmann is wrong. He is very critical of this. Right? So now, just a quick look, and I'll also talk about that 8-5 controversy and all that. That is. So Einstein said, so is.
None of the
Yes, he's not.
yeah, you see. You very
So the thing is, what Einstein said, that his conclusion could be right. So let's forget about how this quantization. Let's assume world is quantized. The world is quantized. Let's take these oscillators to be having energy in terms of h nu, and therefore probability that there will be n excitation would be e raised to n h nu. Probability of n would be proportional to this, and therefore the average energy will be equal to summation n nh nu e raised to minus nh nu over kBt divided by summation n e raised to minus nh over kBt. This is what Einstein did simply. He said this you get to be h nu e raised to h nu kBt minus 1. So he said I'm applying Boltzmann's theory, correct? I'm taking the probability of energy of an oscillator being this to be proportional to e raised to minus e by kBt. Not only he did that, he later, in his 1914 paper, when he introduces A and B coefficients, by introducing stimulated emission, he also derived a different. He's done many of those things, right? And to students, must read Einstein paper. Written with so much clarity. We think Einstein, oh, maybe it's very difficult to read. These are some of the easiest papers to read because it focuses on physics and thinking is very, very absolutely marvelous papers to read. And Since you're in the business of writing papers and you'll be in the business of writing papers, read the second or third paragraph of his paper on not photoelectric effect. Photoelectric is the side thing. It's photon concept. This translation is available in American Journal of Physics. Just like translation of Einstein paper on American Journal. It's one of the best written paragraphs in communication. If you want to be a good communicator, read that. The way he introduces the whole concept is just marvelous. All right. So this is what he does. Now, where does Bose fit in? Although, so Einstein did this was one thing. Then he derives this. This he did in some other context. This was in 1907, and he says, he takes this step.
Yeah. I just have a
Yeah.
question. It is Einstein's this radiation paper and
Astrophysics, yeah.
still in radiation. That has been that came much later than Wien's formula. Looks like the Wien's formula that you is the key in driving and getting ball properly. So when Wien's did that, did he get derive this new key?
Yes. Yes.
And was there any physical?
Yes. Thermodynamics.
Just thermodynamics. Just
Yes, thermodynamics. You cannot be wrong.
So there was no assumption in
Nothing. Thermodynamically derived, so it doesn't care about the details. Gives you a microscope. So it's absolutely exact. Okay. So then Einstein made one further thing. He said, why stop at electromagnetic oscillators? Mechanical oscillators will do the same thing. And he could immediately explain the specific heat of solids going to zero at zero temperature. That's when Nernst actually became, okay with quantum mechanics. Otherwise, he was not. So this is one thing, and then he introduced the photon concept. Now, photon concept was criticized by everybody. As I said, Planck in 1913 was saying this. That is why Einstein got excited by Bose's paper. What Bose did, let me just do that on the side. He said, just like Einstein, he said that Einstein said, let's start with quantized oscillators. Why think about, and then apply Boltzmann formula correctly. So what Bose said is, let's start with the photon gas. Assume they are gas. So his main thing was how to count the number of states this has, right? So he said, so he had to get that formula right. He had to get this 8 pi mu square over c cube right. And in one of the Einstein's biographies, The Subtle is the Lord, in fact, he makes a comment that Bose got rid of that unnecessary electromagnetic thing. So it was purely quantum mechanical. Right? So what he said is that photons have a momentum hv by c, and therefore the number of states is going to be 4 pi dv squared s, so which is 4 pi h square u square h d nu over. Then he said each cell is going to be of the factor h cube. This cancels.
That was revolutionary.
Huh?
That was revolutionary. Volume element as H.
Yeah, as we look back, I think this is how we end up judging the papers. What he did was absolutely marvelous. But there's also a lot of interpretation. It had to be interpreted. And the way he did was counting. This was the number of boxes. And then he says, now in these number of boxes, I'll choose boxes P0, which has 0 number of photons, P1, which has 1 photon, P2, and so on. When he did this, A factorial divided by P0 factorial, P1 factorial, this is the number of ways I can do it. So he's counting boxes, he's not counting photons. And he says that the total energy is fixed. And then he takes different frequencies. Okay, not going to go into that. So he's counting boxes, he's not even focusing on photons. So photons are out, and then he fails 0 photon, 1 photon, 2 photon, infinite number of photons. So photon conservation is out. Then he's not even talking about photons. Any photon can go anywhere. So indistinguishability comes in. All right. So he did all that, and then he took the log and got the right answer. Okay. Now the factor of t, because this is 4 pi. What he had said, to get 8 pi, he knew of Planck's formula. So how to get that 8 pi? He said, let me assume each photon has 2 spin states. And this is what Ghosh has also part of the Ghosh has documented that he had told him. And Einstein got it off and said, let this be a.
Sihiraman also got the experimental proof of photon speed.
Sihiraman was a few years later, he did that.
Nature paper and then
Yeah, so everybody wonders why Bose did not quote that later. Should have. But anyway, I mean, Bose is Bose. So that factor of 2, he later said, you know, the old man cut it off and all that. So that was the factor of 2 and 8 controversy. But there's no controversy. I mean, you know, he had to get that 8 pi factor. But main thing is he got it through photon counting. There's no electromagnetism here. So this inconsistency also goes away. He says photons exist. And if they exist, this is what is going to happen. Right? So this is correct. This is correct. Now I come to Planck. How could he have actually applied this whole thing correctly? He should have maximized something. So this is where I kind of come in and I've decided about that. So what I'm going to say now is, let us assume this formula in distinguishability is correct. So we'll say that between nu and nu plus d nu, there is this energy E. So I'm going to have average energy of the oscillator E nu bar. I can even have the element epsilon nu bar, right? So I'm going to have the number Pn nu, the n nu oscillators, plus P nu factorial divided by n nu plus n nu factorial, P nu factorial, and then I multiply over all these nus. That is going to be the number of ways, total number of ways. And I should, this is the number of ways. I should maximize log of omega with the condition that total E, which is summation n nu epsilon nu is a constant. Given a temperature, energy remains constant. Right? That's what we do. Now, what do I minimize it against? Right? So that is what I'm right aside about. I'll actually minimize it against the average energy. That'll give me the average energy directly. Right? Whereas he got it through Boltzmann's formula right here. This is not Planck's way. This he criticizes, and that does this. I'm following exactly Planck's way. Except that what he could have done is taken all.
Criticizes, so Planck criticizes.
No, Einstein criticized Planck. Then he says that he should be E raised to B E by B kt, and then okay.
So these two features slightly different. Right? So understand that this is if I look at only one single oscillator, ask
What is the average energy?
But this is for multiple.
No, this is also. He says yeah, there are multiple oscillators,
Yeah,
but he finally calculates it procedure. He divides by n. Calculating the entropy
That was the entropic part of it.
per oscillator. Right. So these two approaches are absolutely different.
Yes, that's what I'm saying. They are different. One is particularly treating multiple oscillators
Yes.
at one time.
So what I'm going to do? So therefore, now this becomes summation nu log of exactly the same thing, n nu plus e nu over n nu factorial p nu factorial minus n nu epsilon nu, and I'm going to maximize it with respect to e nu bar. Okay, and in fact this is going to be e nu bar.
Sorry, kind of missed it.
Yeah.
So these large parts, to reconcile these two.
I want to reconcile Planck's way of thinking with Boltzmann's statistics, which he did not do. Right? That's why the title. Okay, now you do this. Obviously, if I'm doing the E nu bar and there's going to be a Lagrange multiplier here somewhere. Right? So to do all this, now you can see when I do this, I'll pick up only one particular nu. whatever new I'm doing about. So rest of the calculation becomes exactly the same as Planck's. And you end up getting a new bar equals precisely. And remember, I have an epsilon nu bar also here because I'm counting the p nu bar. P nu is equal to n nu, p nu bar over epsilon. I'm taking everything nu dependent also.
You are now taking a variation, which he didn't.
He did not. He just counted. You do that, and you get exactly this. Some constant. Okay, and because that constant comes beta, because beta has to be 1 over k, right? So once you get this is the argument. Okay, so
Technically, they will get maximum. They just get the answer for P new. That already that's the thing.
see, he counts in a very funny way. He did not maximize. He just, that's why the criticism was very important.
He is just trying to, kind of match.
Match. He has not
It's
derived
not a
anything.
consistent.
He's not derived anything. The results have to be so. The thing is, he should have matched. That's why I say you want.
He could have.
He could have. Yeah. So he actually could have counted each and every one, kept the total energy the same, and he would have gotten the. You see, his E nu bar comes out in a very funny way. I'm actually getting the formula by doing it, right? And I'm now saying that here's the total energy. Here are different oscillators. Each one has its own element. What should be the average energy of each oscillator so that the number of counts is maximized? Which is absolutely consistent with Boltzmann's picture. This is what you're supposed to do. You do that and you get exactly transformed. Okay, so he could have done that, and this is what I'm excited about. This is important, I mean, from the point of view of that, it fills a historical gap. Now, maybe it didn't occur to him, maybe that's why he got it right, that he counted it correctly. Something he was doing correctly. His conclusion was right. So nobody's criticizing it, except that maybe he missed a few steps. What are those missing steps? That's what I'm trying to do. Okay, and that's where I stop. Well, appreciate your comments because I'm going to send it somewhere. That's why I had to spend time initially what he was doing, because that's very important to know.
So why he didn't do it is, this is like some variational approach.
Yeah, no, the thing is this. You have to realize that Planck, he got this interpolation formula in December. He was not looking at Boltzmann at all. And he was wanted to rush. He was probably desperate. So as soon as he counted and got it, he said, I've got it. I think he did not fully appreciate what Boltzmann was. He just saying count, probably.
Yeah, maybe some other time, because I don't know how many of you know, so our science communicator, she is making a movie on this factor. He's interviewing people and also shooting something at the university. So this, because that time thinking about spin is somewhat obscure. And quantum mechanics is not fully developed. Who will think about spin?
No, he could have, because electron spin was already talking about.
So in 1924, when he was in those days, he probably had a thesis was already there with Einstein. He probably was doing his PhD under Maurice de Broglie. So there was this content between Einstein and de Broglie because Einstein never
In
admitted
fact, the movie will have both the versions.
Right.
Some people think
So
that
spin was
it is a
already
make-up
Right.
story. Those who are great fan of Hudson Rose and wants to glorify it even more, think of all these things.
My thing is very simple. Some
Some
people did it, it's a
think-
beautiful, they really enjoy it.
When the subtle is the Lord, there this has been documented. What exactly Louis de Broglie said about this? The concept of spin was there, Einstein knew it.
Okay.
Yeah.
I think once it has been done, I think you can't take away from great people contribution to both
Right.
great. That whether he got spin right or not, he started quantum statistics. Contribution of Einstein, obviously nobody needs to talk about. It's great, and we are all researchers. we do miss steps. Sometimes we say, ho jayega. Sometimes we say it's easy to show. Former wrote, it's easy to show x and plus y and all that. So I think as students of science, we learn to enjoy it rather than saying who did what, who did what. This is a fascinating story, but I think that's where it should stop.
I have just two questions. One is, do you think that S.N. Bose started thinking that photon is a particle essentially driven by Einstein's photoelectric theory? Because there he exactly used the particle concept.
See, as I said, so I'll give you answer in a very different way. When Heisenberg asked Pauli once, how did Einstein think about general theory of relativity? He said it has been done, enjoy it.
Okay.
That's
And
my
second
approach.
thing is this: exactly at each point, the Fermi-Dirac statistics is qualitatively different at the physical level, not at the mathematics level.
Somebody, one of my friends told me that you should see a appendix of Saha and Srivastava. There actually it says that they had some seeds of Fermi-Dirac. I looked at it, but certainly way of quantum statistical way of thinking of this individual particle was started by.
Yeah, and they will practice.
But by the way, no,
Yeah.
that is also
Symmetry
we actually also tend to quote what we like quoting.
Right.
In Circle of the Lord, he also says that Bose did not make these points. This was interpreted later.
Right.
So, we tend to, people who like, he's our own, so we tend to glorify also a little more. I think let's look at it properly. He did what he did was great. What he missed, he missed. But it doesn't take away from what he did.
It looks like Fermi-Dirac star was proposed by Einstein to S.N. Bose in 1925 when he made it in the Kaiser Wilhelm. That's what Bose does.
Maybe, yeah. So I thank you for your attention.
Yeah. Any other question from the student?
No? Back to DFT tomorrow.
Thank you.